These are all the terms coming in. Same treatment for terms going out. Emitted radiant flux is a fraction of the ideal emitter. And this is going to be epsilon times sigma times the temperature of the surface to the power 4. So this is epsilon I sigma Ti to the power 4. Same idea for E naught. This is a fraction of the amount that is emitted by an ideal emitter. That fraction is given by the number epsilon or epsilon naught. Okay? So this is plus epsilon naught sigma P out to the power 4. And the last one, Q double prime convection, which is plus H naught. Convection from the outer surface to the surrounding fluid. So this is going to be T naught minus T infinity out. Does this make sense to everybody? You see the general idea. Be careful when you draw your arrows. Be careful when you draw your control surfaces. If you understand the implication of what you draw on the control surfaces, this is just straightforward stuff. There are no secrets in these problems. And this is the same equation you're going to see for the rest of the semester. As I typically do in yes, question, yes, go.
So, real quick question. Can you explain why EI and EO are both leaving the surface instead of one of them entering and one of them exiting?
Oh, they are all emitted by the surface.
Okay.
So, whichever is the surface, you just draw an arrow that is going out of the surface.
Okay.
E is always radiant flux emitted by the surface. G is a portion that is absorbed by the surface. So, all the G's will be coming in, all the E's will be going out.
Makes sense.
And that's only if I draw my control surface that way. And as I typically do in heat transfer classes, I don't solve by substituting the numbers and so on. I will leave it at this step. You have been given all the numbers. So this is known, this is known, this is known. And my solution will have all these steps. This is known. All of these are given to us except for T naught. This is the one that we need to find. This is the one that we need to find. This is not an easy equation to solve. It is a fourth order polynomial, which means you need to know how to use MATLAB, which I'm sure you do, or Wolfram alpha. Just take this creature and throw it in there. It will spit out an answer. That's the one you want. Okay? Those are the quantities that you don't know. Substitute, solve. Don't hesitate to use software. Don't do these things by hand. You're not going to gain any bonus points from me. Be most efficient in your work. Okay? The answer, the final answer, check your answers, and my solutions posted will contain all the numerical steps as well. T naught will end up being 277 Kelvin, always. Temperature in heat transfer will be in Kelvin. So all temperatures which means if something is given in degrees Celsius, this is T in Kelvin. So which means essentially I'm looking at 4 degrees Celsius. So the inner side of the window is at 17 degrees Celsius, which was given to you in the problem. The outside is at 4 degrees Celsius. This is a fantastic window, which means that I'm going to have a very, very low thermal conductivity. It's going to trap and make sure that all the good heat in the room does not leave the room. And that's the next step for us to find. And to do this, you can either use 3 or 4 because you have to bring in conductive heat transfer. 3 or 4 is the same thing because we just proved that Q conduction in is the same as the Q conduction out. Okay, so since conduction in is the same as Q conduction out, I can either use information from the drawing on figure 3 or the drawing on figure 4 up there. Use either 3 or 4. So the last step for the problem. I'm going to use 3. From 3, E dot n, always use the equation. E dot n is things coming into the control surface, so this is going to be alpha I gi times ai q double prime times ai. E dot out, things moving away from the control surface, which is going to be ei times ai plus q double prime conduction times ai. E dot stored is 0, E dot generated is 0. So E dot stored, E dot in, E dot out, E dot generated. This is always your standard equation. Take a big axe, cut off E dot stored and E dot generated. E dot in is equal to E dot out, common sense. You don't need to write these things out, but I need to see these steps. Okay? So I have alpha I, which is the same as epsilon I, so I'm just going to write these out. So epsilon I, which is the same as that, times di times ai. I'm just going to call it as a or ai, doesn't matter. Sigma surrounding I to the power 4. This is the net radiant flux absorbed by the inner surface plus convective heat transfer Hi, ai, T infinity I, Ti. All of these are known to us. Surface emissivity is given. Area I don't really care because it's going to cancel off. Sigma is a constant. Hi is given to me. T infinity is the same as T surrounding I. We're just writing these things down. This is equal to Ei ai is epsilon I ai sigma Ti to the power 4 plus conductive heat transfer. Steady state conductive heat transfer in this case is taking place from the left side to the right side. So the temperature T high is Ti, T low is T out. K times area, thickness, which is 2 centimeters given in the problem, Ti minus T naught. Everything is known except for K. You plug in the numbers which I will be doing in my solutions posted on Carmen and find the value. You will end up with K 0.112 watts per meter Kelvin, which is a very low value, which is fantastic for a winter. Once again, this is all just common sense. Heat transfer is common sense. Heat transfer is like cooking. If something is hot, you touch it, the damn thing is going to burn you. There is no secret here. All you need to know are how the equations play out. If you know how the equations play out, one and only one equation in heat transfer, which is this guy.